Hello. Today's lecture will cover Chapter 4, which is on algorithms. This is likely the densest chapter in this course. If you're unclear on any of the material in this chapter, now is the time to ask. This chapter is a fundamental building block that you need to understand for Chapters 5 and 8 later in this class. Algorithms are the foundation of programming. We will focus on imperative programming in this course. Alice is what is known as an imperative programming language. In imperative programming, algorithms are represented as series of commands for a computer to execute. Each line or tile of an Alice program is such a command. This is why you can understand an Alice program by stepping through it line by line. To help you step through algorithms line by line, I'd like to review properties, variables, and parameters for a minute. These are really all the same thing. The differences between these constructs are solely in their lifetimes, where their values come from, things like that. But they're very similar in that they're all little cupboards in the computer's memory where you can store data. They all have exactly one type in Alice, and that type determines the type of data that can be stored in the little cubby holes they represent. Number values store numbers, string variables store sequences of characters, and Boolean variables store truth values. Values are special in that they are what are used to determine whether a branch is taken and whether a loop continues executing or stops executing. So it's important that you understand truth values and that Boolean variables can be used in place of a literal truth value. It's also important to talk about functions now. Functions are kind of like methods and kind of like variables. They're like methods in that when you call a function, when you execute a function, when you try to get a value out of a function, a sequence of commands executes, much like a method. The way they differ from methods is that they return a value of a certain type. So in addition to being able to substitute in a number with a variable that's kind of like x, you can also substitute in a place where Alice needs a number with a function that returns a number. So this is very useful because this is what lets you write things like, for example, if A is less than B, then do this. The less than sign is a function that takes two numbers as parameters and returns a Boolean value. And Boolean values, if you recall, are truth values. So the if statement in Alice needs a truth value, and this function lets you compare two numbers and use the result of that comparison as that truth value. So functions are important. And it is possible for us to write our own functions, but we won't. I'm going to go through some example problems later in this lecture, which correspond closely to the problems that you need to do for homework. However, before I get into that, I would like to go over the Euclidean algorithm with you for a while. The reason I want to do that is because the Euclidean algorithm kind of shows you that there's something more to algorithms and to programming than simply making a computer do things. Algorithms are a part of mathematics. And the Euclidean algorithm really demonstrates that. You don't need a computer to study algorithms. Computers just execute algorithms very quickly, but you can execute an algorithm with your brain, with your mind. And before we had computers, people would do that, and algorithms are kind of part and parcel with mathematics, and the study of them can be very theoretical and very interesting from a mathematical point of view. So, Euclidean algorithm is one of the earliest algorithms ever developed. It's attributed to Euclid. He described it in his book, The Elements, which was written around 300 BC. And a description of it is here. And this is written in mathematical notation, which you might not be familiar with, so I'm going to go through it and kind of translate this. Let a and b be two integers, where either a is not 0 or b is not 0. Start with a and b such that a is greater than or equal to b. These lines are absolute value, but in my implementation and in the proof, I'm going to assume that they're positive. If b is equal 0, then the task is complete and the greatest common divisor is a. So return a. So it's you could implement this in a function because it returns a value given two other values. If you're not ready to return yet, if b is not equal to 0, then you take the remainder r of a and b and store it somewhere. Now, the remainder is what you get when you do division and it doesn't divide evenly. So if you do long division, the number you get at the bottom, if it's not 0, that's the remainder. So the remainder of 7 and 3 is 1, because 7 divided by 3 is 2, and then there's 1 left over because 3 times 2 is 6. So now set a equal to b, set b equal to r, and then repeat. So there's a loop. So Euclid was able to write this out and write it clearly enough that we can understand what he meant today. And he didn't have a computer, but this is an algorithm which is now used in computing fairly frequently. So really you can think of computers as triggering a great interest in the study of algorithms, because computers can execute algorithms very quickly, and so they're more important from a practical standpoint than they used to be. But understanding algorithms is really an end unto itself. Understanding algorithms gives you a better understanding of mathematics. It helps you think more logically. I think it's really good for you. And so I'm glad you're taking this class, because we will at least touch the surface of algorithms. I'm not going to ask you to write anything as complicated as this. But I do want you to get a little bit of experience writing some very basic algorithms. So the first thing I'm going to do, since we're talking about Euclid's algorithm, is I'm going to implement Euclid's algorithm in Alice. Alice is a programming language. Yes, it's a toy programming language. Yes, it's mainly intended for doing animation. But there's no reason that I can't implement this algorithm in Alice. Alice is a real enough programming language to where I can do this and it'll work. So let's get started. Alright, so we're going to start with A and B such that A is greater than or equal to B. Okay. So I've got a world with a bunny in it, and the only reason the bunny is here is to say the result. So I've got my method here, and I've got all my variables already defined and printed out. So I'm going to set the value of A to 0, but not really. What I'm going to do is I'm going to set the value, I'm going to ask the user to enter a number. And then that's going to be A. And now I'm going to ask the user to enter another number for B. Because without that, how are we even going to get started? We need to have some A and some B to where we can execute this. Now the algorithm assumes that A is greater than or equal to B. So I'm going to check to see if that's true, and then swap them if it's not. So remember I said A less than B is a function? Well, here it is. Expressions A, expressions B. If A is less than B, then what I want to do is I want to swap them. So swapping two numbers is actually a tiny algorithm in itself. And the way it works is this. First, you take a temporary variable and you set the value to A. And so now you have the value of A backed up. So now that you have the value of A backed up, you take A and you set the value to B. And so now A is swapped. A used to be A, and now A is B. So we've done half the swap, so now we have to do the other half. We have to set B to the value of A. So we say, okay, B set value to A. Is that what we want to do? Think about it. We want to set the value to temp, because temp is what A used to be. A is now B, and so we can't set B to A because we already set A to B. So A now, remember they're cubby holes, and we already changed the value of the cubby hole A and put B in it. So we have to set B to the temporary variable that we had earlier. So I've done my swap now. So now we're ready to start with the algorithm proper. So let's take a look at it. Alright. So I'm going to run this algorithm while B is not 0, because it says if B equals 0, then the task is complete and the GCD is A. So while B is not 0, I'm going to run the algorithm. So while B is not equal to 0, while B not equals 0, what do? I take the remainder R of A and B. So I've got R here. R I'm going to set to the remainder of A and B. Now what's this function here? Well, it's something I wrote because Alice didn't provide something that I needed. So I wrote it myself. This is this function here, and this is just code. Looks more complicated than it is. All it does is it gives you the remainder of two numbers when you divide them. R is the remainder of A and B. So now it says set A to B and B to R. So okay, so I'm going to take A, set it to B. I'm going to take B, set it to R, and then I'm going to keep going. So once this loop stops, A contains the greatest common divisor. And so I'm going to make the bunny say that. So outside of this loop, I'm going to have bunny say, want bunny to say A, however, the say function only takes things of type string. So you can't say a number because a number isn't a string of characters. Fortunately, there's a function we can use here called whatAsString, which gets around that problem. So I can say A as string here. So now let's play this world and see if this works. Right. What's the greatest common divisor of 12 and 8? Should be 4. Lo and behold, it is. What's the greatest common divisor of 45 and 4? 1, because they're coprime. There's no common divisor other than 1 of those two. What about 8 and 8? Obviously 8. What about 9 and 3? Should be 3, because 9 divided by 3 doesn't have a remainder at all. 3. Alright, so this bunny is very smart now, at least for a bunny, and he's given the right answer. So it looks like this algorithm is working. So now the question is, why does this work? And you will find that given a description of an algorithm, even a vaguish English description of an algorithm, you can write it out and make it work right on the computer without really understanding on a deep level why the code you're writing works. So this site is proofwiki.org, and it's Creative Commons license, so I can use it in a lecture. And it gives a proof of why this works. So okay, suppose, and this is written again in mathematical notation, so I'm going to translate this for you. And we'll go over this proof so that you understand why this algorithm actually does what it's supposed to do. Alright, so suppose A and B are integers. This EZ thing, this means suppose A and B are elements of Z, and Z is the set of all integers. So suppose A and B are integers, and either A or B isn't 0, so they're not both 0. Then, from the division theorem, A equals QB plus R, where 0 is less than R is less than B. And this is absolute value of B, but we're not going to deal with negative numbers here, because that just complicates it. So for any integers A and B, for some Q and R, this holds. So say it's 9 and 4. Alright, well 9 equals 2 times 4 plus 1. So Q is 2 and 4 is 1. Now, from the GCD with remainder theorem, the GCD of A and B is also the GCD of B and R. So that's why we ignore Q up here. We don't need to worry about Q, we only need to worry about the remainder. So let's look at that, because that might not be obvious. Why is the GCD of A and B the same as the GCD of B and R? That doesn't necessarily make sense. So let's look at it. And let's look at it here. Okay, so we've got, what's the theorem say exactly? Let A and B be elements of Z, and let Q and R be elements of Z. So let A, B, Q, and R all be integers, and have them be the A, B, Q, and R such that this equation holds. The assertion then is that the greatest common divisor of A and B is the same as the greatest common divisor of B and R. So let's say that the greatest common divisor, so we start with the greatest common divisor of A and B divides A, and it also divides B. Now, we know that from the definition of common divisor. If GCD of A and B, if this number is the greatest common divisor of A and B, then it is a divisor of A, and it is also a divisor of B. This little hat thing means and. We're going to get into this a little bit in Chapter 5, the little hat stuff. So now we know, from this, we know that the greatest common divisor of A and B also divides A minus QB for any integer Q. Now, why do we know that? Well, there's another theorem that tells us that. So, theorem is, let C be a common divisor of two integers A and B, then C divides A and C divides B, then C divides any integer combination of A and B. So for any P and Q, C divides PA plus QB. So you can multiply A and B by anything, and as long as you multiply them by integers, this common divisor you have is a common divisor of the combination, of the integer combinations of them. So proof one assumes that you know a lot of mathematics, but proof 2 is pretty simple. So we have that C divides A, and so therefore there is some value x, which is an integer, such that A equals xc. And that's by the definition of what a divisor is. There's also some integer y, such that B equals yc, by the definition of divisor. Therefore, for all integers P and Q, PA plus QB is equal to P times X times C plus Q times Y times C. And that's by substitution of these two values. If these two are equal, you can just substitute the values. Therefore, you can factor out the C, and therefore for all integers P and Q, Px plus Qy times PA plus QB equals Px plus Qy times C, because of distribution. Therefore, there is some integer z such that PA plus QB equals ZC, because we know that Px plus Qy is an integer. Therefore, C is a divisor of PA and QB. And remember, P and Q could be any integers. So we just proved it. Now, does that really give you any insight into why this is true? Because this is kind of a deep concept. But if you think about it, it's kind of obvious too. If you have some number that divides 6 and divides 4, then if you have any multiple of 6, that's just a whole bunch of whatever you divided it by. And if you also have 4s, that's just more of what you divided it by. So this is kind of proving a little bit of an obvious thing. So let's look back at here, because, and that's what we're using here. So if it divides b and it divides r, it also divides qb plus r, meaning it also divides a. I'm sorry, we were up here. So divides a minus qb, meaning it divides r because r equals a minus qb, meaning that the greatest common divisor of a and b is less than or equal to the greatest common divisor of b and r. Now why is this? Because it's the greatest common divisor of a and b by definition, and it also divides b and r. So because it is a divisor of b and r, because it's a common divisor of b and r, then the greatest common divisor of b and r has to be at least as big as the greatest common divisor of a and b. And so now let's look at the other way. Greatest common divisor of b and r divides b, and it divides r. Therefore, it also divides qb plus r, because a common divisor also divides any integer combination. Therefore, it divides a, because a is qb plus r for some q and r. And therefore, greatest common divisor of a and b is at least as big as the greatest common divisor of b and r. Well, if something is less than or equal, if a is less than or equal to b and b is less than or equal to a, then a equals b, obviously. So, therefore, these two are equal. So that's the proof of GCD with remainder. So now let's look at the proof of the algorithm. So because these two are equal, we can instead search for the greatest common divisor of b and r. Now r is less than b, and b is an integer. So therefore, r will eventually be 0 if we keep looping. And we will eventually stop. Now why is that? Why is r less than b? How do we know that? Well, because r is the remainder of a divided by b. And so if r is greater than b, then it's not the remainder, because you can take a b out of it, and then you'll have a smaller remainder. Does that make sense? It's just long division again. The remainder of 9 divided by 4 has to be less than 4. Because if it is 4, then you can take another 4 out of it. So we're getting smaller as this loop continues. We'll look here at this loop. As this loop continues, r is getting smaller, and because b is being set to r, b is getting smaller. And if b is getting smaller, eventually it's going to be 0. And therefore, the algorithm will stop. And when r is 0, the GCD of r and 0 is r from GCD with 0. For all a, where a isn't 0, the GCD of a and 0 is a. Every integer, why? Because every integer divides 0. 0 divided by 5 is 0. 0 divided by a million is 0. Every integer is a divisor of 0. So the greatest common divisor of 5 and 0 is 5. Because 5 divides 5, and 5 divides 0. 0 divided by 5 is 0. 5 divided by 5 is 1. Neither of them have a remainder. So more intuitively than this, you can think about it as we get to a point where there's no r. You can also stop where r is 0, and a equals qb. Because now b divides a, because b times some integer is equal to a. So by the definition of division, b divides a when there is no r. So once we get to r equals 0, then it's b. But the way we implemented it, well, the way we implemented it, that actually is where we stop. We stop where b is 0. And then we say a. So we could have stopped a little bit earlier. We stopped at this point, but we could have stopped a little earlier. We could have stopped when a is something and b is something, in a slightly different implementation than what we have. But just understand that the remainder is getting smaller. Once the remainder is 0, the greatest common divisor is of a and b is b. Alright, so once we stop looping, we've got the greatest common divisor and it's stored in a. And so we have the bunny say a as a string. And the bunny is telling us the greatest common divisor. So I'm going to save this as gcd.a2w. And I'll post it online. So let's continue with the slides now. Okay. I am going to go over the sample problems, but I'm also going to go over the tutorials. So this tutorial on branching is going to come in really handy on your homework for Chapter 5. You're not going to be using branches in the homework for this chapter because we're going to focus on loops, but we will use it for Chapter 5. Alright, so we've got our linear sequence here. And I guess I'll start with triple jump, not triple jump with parameters. White Rabbit, Cheshire Cat, and Alice Little. So what we're going to do is we're going to ask the user which one of these characters we want to jump. So we're going to put an if-else in here. So if, and now we're going to ask the user a question, ask the user for a Boolean, ask user for yes or no. Yes or no means truth value, so we can substitute in that function here because we want a truth value for the branch condition of an if statement. Do you want Alice to jump? So if the user does want Alice to jump, well then, by golly, Alice is going to jump. Otherwise, we need to ask which of the remaining characters we want to jump. So ask the user again for yes or no. Well, we need to put another if in here. You can nest ifs inside of each other, so this is if, else, if. which is a fairly common pattern. Ask the user, do you want the white rabbit to jump? If yes, then, well, the white rabbit jumps. Otherwise, well, someone's going to jump, because we're not going to let the user not have anybody jump. We want someone to jump, so if the user doesn't want Alice to jump, and the user doesn't want the white rabbit to jump, then the Cheshire Cat will jump. So let's play this world and see what happens. Do you want Alice to jump? Yes. Okay, she jumps. Great. Start over. Do you want Alice to jump? No. Do you want the white rabbit to jump? Yes. Alright, white rabbit jumps. Do you want Alice to jump? No. Do you want the white rabbit to jump? Again, no. Okay, well, now the Cheshire Cat jumps. So this is a fairly simple, very easy program. And it shows you basically how branches work. Do you want, if this condition is true, so if the user selects yes, make Alice jump. Otherwise, if this condition is true, you want the white rabbit to jump, then make the white rabbit jump. Otherwise, make the Cheshire Cat jump. So this is kind of a silly example, just to demonstrate how branches work. And we'll get into more complex branches later, like what you can actually do with these, because they're a fundamental building block. But for now, that's all for branches. So now, we're going to talk about loops. I'm going to go through tutorial 4B, triple jump with parameters, and I'm going to go ahead and set the height here to 1 instead. Actually, we don't need triple jump with parameters. We can still just use triple jump. So now we've got our triple jump here. And what we're going to do is we're going to make them all jump at the same time. And we're going to make them jump a number of times. So to make them all jump at the same time, you just use a do together. Now, there is such a thing as concurrent programming. The book talks briefly about it. It's very hard, and this is not really concurrent programming. I mean, it is, but it's also not. It's an extremely simplified form, and the reason for it isn't really to allow concurrent algorithms. It's just to make it so that more than one thing can happen at a time in the Alice world. So now we're going to add a count-controlled loop to the world. And the way to add a count-controlled loop is we're going to use the loop instruction here. So it says drag a loop tile from the bottom of the editor and put it just below the do together tile. Now how many times do we want to loop? Well, let's say 5. And now let's drag the do together tile into the loop tile. So that's making this inside of this tile, one tile inside of another. So the way to look at this is, okay, loop 5 times, show the complicated version. It's always good to show the complicated version. On your homework, if you are using a loop instead of a while loop, I want you to show the complicated version so that I can make sure that the loop is doing what it looks like it's doing. Because the simple version can actually, if you like change stuff here, then this is ambiguous, because it doesn't actually loop 5 times if you increment by 3. Think about how many times it will loop. So anyway, just show the complicated version. Loop index from 0 up to but not including 5, incrementing by 1. So this is going to loop where the index is 0, 1, 2, 3, and 4. And we're not using the index for anything, so the index doesn't really matter, except that it's how the computer figures out when to stop looping. So if we loop 5 times, what's going to happen? Well, they are going to jump 1, 2, 3, 4, 5 times. Sure enough. So now we're going to do basically the same thing, except that we are going to use a while loop instead of a loop loop. So to do that, first we get rid of the loop loop. So I took the body of the loop, which is this set of instructions that make them all jump together, and I still have that. And I'm going to create a new variable called count. And count is going to start at 0. Now I'm going to drag the while instruction in here. And now just like if, while takes a truth value. Now what's the truth value do we want to use? Well, see if you can guess what the truth value here should be. If we wanted to make it loop 5 times, well, we're going to use a less than b, and we're going to say count less than 5. While count is less than 5, do this. Now there's something we're missing here. Think about what's going to happen if we run this as is. Count is 0, while count is less than 5, do all this. Alright, so it's going to check if count is less than 5. It is, because 0 is less than 5. Alright, now it's going to make everybody jump. Okay, now back up to the beginning, because this is a loop. Is count less than 5? Yes, it's still 0, and 0 is less than 5. So take a guess as to how many times this loop is going to execute. The answer is infinite. They will never stop jumping. I mean, I guess eventually the computer will break and they'll stop jumping, many years from now, but they're never going to stop jumping on their own. Because count will always be 0, and 0 will always be less than 5. So this is not what we want. We wanted them to jump 5 times. So what we need to do is we need to use count to remember how many times we've already jumped. So to do that, we're going to set count to count plus 1 each time. So now what are they going to do? How many times are they going to jump? Let's see. Alright, 5, which is what we wanted. And so we are done here. And now I'm going to go through the example problems. Make a bunny turn in a circle a number of times equal to the length of a pier in meters. Okay. So I'm going to start with a new world, and I guess I need to put a bunny in it. And I guess I also need to put a pier in it. So where might a pier be? Well, maybe it's over here in environments. No, doesn't look like it. Environments, furniture, beach. I'll bet it's on the beach. Yes, here we go. Here's a pier. Alright, so for some reason, who knows why, we want to make the bunny turn in a circle a number of times equal to the length of the pier in meters. Well, obviously, we will need a loop for that. And we want to loop up to but not including the length of the pier in meters. So that's going to be a function of the pier. Pier's width, pier's height, pier's depth. So let's say the depth of the pier. That's probably the height. It's not the height, it's not the width, so it must be the depth. And actually, loop from 0 up to but not including the depth of the pier, incrementing by 1. And what do we want to do? Well, we want to make the bunny spin. It's going to be a method of the bunny. Bunny turn left 1 revolution. So he turned a number of times equal to the length of the pier in meters. So that worked as it's supposed to be. So our example problem 1 is finished. Example problem 2. Make a spaceship count down to 0 and then take off. So this will be a little more complicated. So first, let's set up the environment. We're going to be in space now, and we're going to want to add a space object. So we want a spaceship. So let's see if we have a better spaceship. No, we could use the lunar lander, but I guess let's use the spaceship. Why not? Alright, so I'm going to go ahead and turn it so that it's facing us. And done. So the spaceship is on the ground, so we're going to make it count to 0 and then turn off. So to make it count, well, the spaceship's going to have to say things. To make it count to 0, well, we're going to need a loop. So let's create a variable called count, and let's start it at 10, because we want them to count down from 10. So, as long as the count isn't 0, we want the spaceship to continue counting down. Once the count gets to 0, we want the spaceship to lift off. So think in your head about how we should go about doing that. We're going to need a loop to count down, and then after the loop has finished, we're going to need some extra code to make the spaceship lift off. Think about why. This is how you come up with algorithms. This is how you do programming. You think about, okay, what do I want to happen? And now how do I break that down into steps for the computer to execute to make what I want to happen happen? So I've got tools. I've got statements, method calls, function calls, if statements, loops, all of that type of good stuff. And some combination of all of that will make what I want to happen happen. So here what I want to happen is I want that spaceship to count down from 10 to 0 and then take off. So actually, instead of making it say 0, let's make it say liftoff. Just for better effect. So we're going to say, use a loop to count down. So while, and remember, we've got this function, these functions, while a greater than b. We're not going to use less than b this time, we're going to use greater than b. So while count is greater than 0, I'm going to make the spaceship say the current countdown. So remember, I can't make him say numbers, so I have to make him say what as string, the number as a string. So see, we've got what as string here. Spaceship say count as string. It's going to say 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And now, remember I said I wanted the spaceship to say liftoff. So after this loop is done, once we've counted down to 0, make the spaceship say liftoff, and now we have to actually make the spaceship take off. So the spaceship is going to go up, and let's make him go up 5 meters. See how that works. Let's play this world, see what happens. What did I miss? I missed something. What did I miss? Have to decrease count. Decrement count by 1. Because I'm going down by 1, I can use this special instruction to decrement count. Normally, I would have to set count to count minus whatever, but I can decrement count this time. So, alright, I want him to lift off a little bit more. Let's make him move up 10 meters instead. But other than that, this was basically perfect. So that concludes our example problem 2. Okay, he still didn't quite lift off too much because I can still see the bottom of the spaceship, but we don't care. Example problem 3. Make Alice spin and count to 5 by fourths. So what I want here, first let's go back to a grassland. I want to add Alice to a world and make her spin and count up to 5 by fourths and then stop. So for that, I need Alice. Alice is a person, so she's going to be in here. Alice Little. Move her to the center of the screen. Make her face the camera. And now we're done with that. So, we're going to make her count to 5 by fourths. So let's start at 0, let's say. So we're going to have a count variable, and it's going to be 0. So we need a loop now because she's going to be spinning and counting up. So first, we're going to make her say current value of count. Now we've done this so many times, I'm sure you know what we have to do to make this work. Make her say count. And now that she said count, let's make her spin. So she's going to turn left all the way around. Now, what do we have to do? Well, first we have to change this from while true to something else. We want her to count up to 5. And let's say we want to include 5 in the count. So in that case, we need this one, while a less than or equal to b. So while count is less than or equal to 5. What else do we have to do? Think about it. We need to increment count, or we need to increase count. But we can't increment it. We have to set the value to count plus 1/4, because we want her to count up by fourths, not by 1. So she's going to say 0, 0.25, 5.75, 1, and so on. So this is going to take a while. So I'm going to speed this up. And that worked very well. So that's example problem 3. So now revisit example 1 and replace set count to count plus 1 with increment count by 1. So that one was the bunny with the pier. So we'll recreate that so that we can change this. Pier was in the beach. And we'll put a while loop, create a count variable, start it at 0, and while count is less than count. Is that ever going to be true? No, it's not. Length of the pier, or rather depth of the pier. And everything in Alice is in meters. Every distance is in meters. So while we're going to do that, we're going to have the bunny spin, meaning he turns left 1 revolution all the way around. And to increment count, we don't use this because it's explicitly told us not to. we set count to the value of count plus 1s. So the increment is a convenience instruction, but this is how you can really do it. So let's make it happen. Looks like the pier is about 11 meters. And that concludes example 4. So this is the end of my lecture on algorithms. I encourage you to study this material very carefully. Do the homework, but don't just do the homework. Make sure you understand why all of this stuff works the way it does. And when you do the homework, practice thinking about how you can write programs to do what you want to do, to make what you want to happen. Because this chapter gives you all the tools you need. And the Chapter 5 homework is going to be to write a guessing game. It's probably the hardest homework in the class. You have 2 characters, and they come up with a number, random number, and I'll give you a function that can generate a random number. And they ask the user for a guess, and as long as the user guesses wrong, they give a hint. So if the random number is 65, and the person guesses 40, one of the characters says, "You guessed too low." If they then guess 80, the other one says, "You guessed too high." And so, because of these hints, the user can eventually figure out what the number is. So it's a simple guessing game. And I want you to think about how you might go about programming that. You're going to need a loop, and you're going to need branches. So they're both important. So with that, I will let you go. Goodbye for now.